So today we are going to introduce the concept of mathematical induction. Okay, I'm going to give you the basics today, and then tomorrow we'll actually go through the process of writing a proof using mathematical induction. Yes, you heard me right. We are going to write a proof. Okay, now, these are not your two-column geometry proofs, okay? If any of you go into upper-level mathematics, like mathematics and calculus, or in college past calculus, but that aren't engineering-based, you are going to write a lot of proofs, okay? That's what pure mathematics is, figuring out what's true and what's not, okay? You will never write a two-column proof again. That's not how proofs really look like, okay? There's some different strategies that we can use when we prove things, and one of them is called mathematical induction, okay? So let's go ahead. Okay, in math, we like to know whether things are true or not. Now, some of you may be okay with me just telling you things, okay? But really in math, we need to understand why things are true, and we need to be able to prove that things are true. So mathematical induction is a proof strategy that is based on a sequence, which is why it's in this chapter. Okay, feels very random, but it is not. By the end of tomorrow, you're going to be able to prove to me that this is actually true. If we add up this sequence, 1 plus 2 plus 3 plus 4 plus 5, all the way up to n, okay? It's basically the arithmetic sequence n, and we add up all the terms. That is the same thing as taking n times n plus 1 over 2. Tomorrow, you will be able to prove that to me. Okay? Those are the kind of things that we are going to be doing tomorrow. Okay? Today, we're going to lay the foundation. Okay? So, you are going to get a statement involving a positive integer n. Okay? Kind of like I've given you up here. You're going to get a statement involving n. This formula equals this shortcut. So I'm going to tell you the process of what we will do, and then I'm going to go into some detail explaining why it is logical for us to take these steps. First, we're going to show that P of 1 is true. We're going to plug in 1 and make sure that it is true for n equals 1. Then we are going to prove that for every integer k, yes, we have to change the variable. For every integer k, then if P of k is true, then it needs to make the k plus 1 value true. Go ahead and let you write what you need to down. That way you don't have to write and listen to me talk at the same time. So we're going to plug in 1 and make sure that it's true for 1. Then we're going to assume that it is true for k, okay, different variable, k instead of n. We're going to assume it's true for k and then show using some algebra that it is going to work for k plus 1. Okay? If we can do that, then our statement in terms of n will be true. Okay. Why does this make sense? Okay? I want you to think of dominoes. Okay? What happens when you set dominoes up like this and you knock one over? They all fall down, right? Okay, so essentially what we are doing is we are saying we're going to set up our dominoes and we're going to say our first one is going to fall. Okay, that's us plugging in 1 and making sure that it's true. If we can verify that that first domino is going to fall down, and we can show that any domino in our line is going to knock over the next one, okay, then when we push that first domino, it's going to knock over the second one. And the second one's going to knock over the third one. And the third one's going to knock over the fourth one. And the fourth one's going to knock over the fifth one. And they're all going to go down. Okay? So we're creating a domino effect, essentially. We're going to prove that our first statement is true. Plug in 1. Then if we can show that the k term makes the next one true, k plus 1, then all of them are going to be true. If 1 is true, then 2 is true. If 2 is true, then 3 is true, etc., etc. We have our domino. Does that seem logical? Anyone have questions about that explanation? So today we're not actually going to write any of the proofs, okay? We're going to save tomorrow for actually constructing the proofs. What I want to do today is practice the notation and the difference between the k and the k plus 1, okay? That way tomorrow when we have to construct our proof, we kind of have a vision of what things are going to look like as far as the algebra is concerned, okay? So let's go ahead and do this. Go ahead and write this down. Now I'm giving it to you in terms of k already. Okay. Tomorrow you will get statements in terms of n, and then we'll have to use k in our proof, but right now I'm just giving you things in terms of k. If this is the piece of k statement, I want us to write the piece of k plus 1 statement. What do we have to do to write that? Okay, anywhere there's a k, we're going to put a k plus 1. It is as simple as that. So we are going to have 6 over, instead of k, we are going to write k plus 1. And instead of k plus 3, we're going to have k plus 1 plus 3. But really, we can just write k plus 4. This will be something where tomorrow we're going to start here, and this is where we have to finish. So knowing what that k plus 1 term is going to look like is going to help us with our algebra know where to stop. On the other side of the equation, remember, we're going to have something that looks like this. So you're going to have like a sequence that's added up, and it's going to equal an expression. Okay? So here we practiced the expression, let's go ahead and practice rewriting a sequence. Okay, so go ahead and write this down. Okay, so I want you to notice that this is the sum of the terms of our sequence 3k minus 1. Do you see that? 2 plus 5 plus 8 all the way up to 3k minus 1. That is the sum of the arithmetic sequence 3k minus 1. Okay. Now, let's look at our k plus 1 sum. All right. 2 plus 5 plus 8. Does that get affected? No. Here, we have 3 times k minus 1 minus 1. If we're looking at the k plus 1 sum, what happens to this k minus 1? K plus 1 minus 1 is essentially what it is, which is going to go to k. So what we have is 3k minus 1. Here, when we replace k with k plus 1, we have 3 times k plus 1 minus 1. So I would rewrite this as 2 plus 5 plus 8 plus ... 3k minus 1, and then 3 times the quantity k plus 1 minus 1. If we go ahead and distribute that 3 through, what is that term going to be? 3k plus 2. Now, something that we will work with tomorrow (2 plus 5 plus 8 all the way up to 3k minus 1. Do you see that somewhere else on that page? Sarah, where do you see it? Very top, right? That's what we started with. Okay. Tomorrow we're going to work with that, and we're going to have a way to algebraically manipulate what's happening up here. All right, now we're just practicing the k plus 1. But tomorrow we'll be able to actually replace that with something. Okay. All right, this one is for you. What I'd like you to do is write down piece of k, and then write down piece of k plus 1. When you have it, I'd like you to turn to your neighbor and compare your answer. When you have it, turn to your neighbor and compare your answer. Gabe, what do you have?
Should I square the things out, or should I have left them squared?
You should leave them.
Okay, I have k plus 1 squared times k plus 2 squared over 4.
Okay. So Gabe, I'm glad you asked that. I want you to leave it like this, okay? Your piece of k and piece of k plus 1 should have a similar format. If this is not multiplied out, then you don't want to multiply this out, okay? All right. Okay. On your gold sheet, you have 1, 2, 3, 4, 5, 6 problems. And we have 6 minutes left. I challenge you to get these 6 problems finished in the time that we have left.